Hello everyone. Today I am going to discuss about acidic nature of alcohols and phenols. Acidic nature of alcohols and phenols. Alcohols and phenols are acidic in nature. That can be known by some chemical reactions. Alcohols ROH on reaction with sodium metal, a highly electropositive metal, more reactive element, will give us RONA, RO minus Na plus, and liberates half mole of H2 gas. So the compounds which liberate hydrogen gas on reaction with sodium metal are said to be acidic. And it could be compared with HCl. HCl, if it is reacted with sodium metal, it will give us NaCl, a salt, plus half mole of hydrogen gas. See why this HCl is giving us a hydrogen gas, why it is liberating hydrogen gas, because this HCl is acid. It is known to us. All the protonic substances on reaction with sodium metal liberates hydrogen gas. In the same way, so this alcohol is liberating hydrogen means this alcohol it is also acidic. So this reaction proves that the alcohols are acidic in nature. And to know that alcohols are OH, if they got ionized, the OH bond being polar, ROH will be ionized to give us RO minus and H plus ion. So if it ionizes, it will give us alkoxide ion and a proton. So we know that all the chemical species which gives H plus ion by ionization are usually considered as acids. So this alkoxide ion is less stable. See, let us go to the acidic nature of primary, secondary and tertiary alcohols. I am taking ethanol CH3, CH2OH. If this is ionized, it will be giving us ethoxide ion CH3, CH2O minus and H plus. If I take another alcohol CH3, CH3OH. If this one is ionized, it will be giving us CH3, CH3O minus plus H plus. This is a primary alcohol and this one is a secondary alcohol. I am going to take a tertiary alcohol this time for comparison of acidic nature of this primary, secondary and tertiary alcohols. So this tertiary alcohol, when ionized, it will be giving us CH3, CH3 and O minus plus H plus. We got ethoxide ion and isopropoxide ion and tertiary butoxide ion. 3 alkoxide ions are obtained. And now, to know the acidic nature of these corresponding alcohols, we need to check the stability of alkoxide ions. In ethoxide ion, the oxygen-linked carbon is having one CH3 group neighboring to that. Alkyl groups or CH3 groups, basically they act as electron donating groups. Here oxygen is having 3 lone pairs and the electron density is some more increased by a methyl group. So because this methyl group is an electron donating group. So the electron density will be increased on this carbon, which may be throwing some electron density onto oxygen. And the alkyl group's presence on this carbon, they make the oxygen to be rich in electron density. And here, if you look into secondary alkoxide ion, so it has 2 alkyl groups linked to the oxygen-linked carbon. So even they increases the electron density by a greater extent than in the case of primary alkoxide ion. So the secondary alkoxide ion, it experiences greater electron density. And in case of tertiary alkoxide ion, so there are 3 alkyl groups linked to the carbon which is linked with oxygen. So here all the three alkyl groups will contribute electron density. They will increase the electron density on carbon, which in turn may be increasing the electron density on oxygen. So oxygen electron density will be increased by even by greater extent. So wherever there is a possibility of decreasing the electron density of oxygen, that kind of alkoxide ion will be more stable. In which cases among these three, the primary alkoxide ion will be having relatively less electron density, not less electron density. Less alkyl groups are present on primary alkoxide ion. The secondary alkoxide ion having more alkyl groups, so more electron densities, it will be absorbed there. And in case of tertiary alkoxide ion, the electron density on oxygen will be more. So this is highly unstable. Greater the stability of alkoxide ion, greater will be the acidic strength of its corresponding alcohol. So this is less stable, highly unstable. Right? And this one will be relatively little bit stable. And this is this one, primary alkoxide ion, is even more stable. So according to that, primary alcohols are acidic, they are strongly acidic. Then secondary alcohols, and then tertiary alcohols. So this is what acidic strength of alcohols. Okay, this is what the correct order of acidic strength of alcohols. Primary alcohols will be more acidic, then secondary, and then tertiary finally. OH. If I have a NO2 group here, say for example if I have a H here, this NO2 group acts as electron withdrawing group, and it will work as electron withdrawing group by minus or effect. If I take ethanol, CH3, CH2, OH, compared with this compound is more acidic. That's what nitroethanol is more acidic than ethanol because of presence of electron withdrawing groups. How the electron withdrawing groups increases the acidic strength of these alcohols. The acidic strength of alcohol will be more if the electron density of oxygen is withdrawn by some X group present on the carbon. So this nitro group will be trying to pull the electron density around carbon, and which may be decreasing the electron density of carbon, and that electron density, to rectify that lost electron density, carbon is now trying to pull the lone pair of electrons from oxygen. As a result, now the oxygen suffers from electron deficiency. Now the oxygen is more interested to take away the OH bonded sigma pair of electrons. As a result, this bond pair of electrons may be completely taken away by oxygen, and then H will be released as H plus easily. So by that way, the electron withdrawing groups increases the the acidic strength. Say for example, if you are given some questions like this, CH3, CH, Cl, OH, CH3, CH, OH, here is my F, CH3, CH, Br, OH. That's what bromoethanol, fluoroethanol, chloroethanol. Three compounds are given if about acidic strength if a question is asked so. So these halogens linked here acts as electron withdrawing groups by showing minus I effect. Because the halogens being more electronegative elements, the sigma bonded electron pairs are pulled towards halogens, and where they decreases the electron density around this carbon, and now the carbon may be pulling the electron density present in the sigma bond between C and O. That decreases the electron density on oxygen, and by which the OH bond sigma bond pair of electrons may be strongly pulled towards oxygen. As a result, H plus ion can be easily released. The H can be released as H plus ion. Now, greater the electronegativity of the halogens present on the OH linked carbon, greater will be the acidic strength, or more the number of halogen atoms linked on the OH present carbon, more will be the acidic strength. Here, fluorine, here is bromine, here is chlorine. All the alcohols are having monohalogenated substitutions, and out of these three, F is being more electronegative, which show greater negative inductive effect. The sigma bonded pair of electrons are strongly pulled towards fluorine. so which decreases the electron density of oxygen by a greater extent. So that this is expected to have greater acidic strength among these three. So I can write, if I label this as 1, 2, 3, right? So I can write the correct order of acidic strength 2 greater than 1 greater than 3. Because electronegativity is more for fluorine, and then is for chlorine, and then is for bromine. So greater the electronegativity, greater will be the withdrawing tendency of the sigma bonded electron pair by minus I mechanism, negative inductive effect mechanism. If I go for one more example, I'm taking CH3, CHCl, OH. I'm taking this one, CH3, CHCl2, OH, and CH3, CF2, OH. I have three compounds here, among which the OH linked carbon here is having 2 fluorine atoms. There it should be like this should be like CCl2. It has 2 chlorine atoms. It has only 1 chlorine atom. Greater the substitution of halogens on the OH linked carbon, more will be the acidic strength. So definitely you can write the correct order of acidic strength of these compounds, right? So third one is more acidic in nature, third alcohol, and then second one, and then least is third one. Say I'm taking one more set of examples: CH3, CHClOH, CH2Cl, CH2OH, CHCl2, CH2OH. If I look at these three examples, in these compounds, the halogen atoms are present directly on the OH linked carbon, and here the halogen atom, one halogen atom is present on the neighboring carbon to which OH group is linked, and 2 halogen atoms are present on the neighboring carbon to which OH group is linked. So if you look at that, closer the position of halogen to the OH linked carbon, more will be the impact of negative inductive effect. So that causes greater impact on acidic strength. So based on this, first compound is expected to have greater acidic character. So based on this, I can say first compound is more acidic, and then this one third, and then least is about. Next, moving on, discussing about the acidic strength or acidic nature of phenols. Phenols are basically acidic in nature. They can release 1 proton by ionization. If phenols are reacted with sodium hydroxide, NaOH, an alkali, aqueous NaOH, they will give us sodium phenoxide salt, O minus, Na plus, and water. This reaction confirms that this is base is known to you, and this must be an acid because we are getting a salt and water. So simply this is a neutralization reaction. A neutralization reaction happens when we react a base with an acid. So definitely if we are getting a salt and water, it must act as an acid. Right. And one more thing, that if phenol is reacted with sodium metal, to check the acidic nature of that compound, it will be liberating hydrogen gas, similar to the previous case. Phenol is forming a sodium phenoxide and giving us half mole hydrogen gas. So it confirms that the phenols are acidic in nature, and they can release a H plus ion when they are dissolved in the polar solvent. But let us check into the stability of and the acidic strength of the phenols, right? So in phenols, OH group is linked to benzene ring. If it is ionized, we will be getting a phenoxide ion, O minus, O with 3 lone pairs, a phenoxide ion, and H plus. So this is a phenol, O with 2 lone pairs. Phenol, on losing 1 proton, it will be giving us 1 phenoxide ion and this H plus over 3. And now checking into the stability of phenoxide ion. If this phenoxide ion, this is known as a conjugate base, and this is acid. According to Bronsted acid-base theory, acid upon losing a proton will be forming its conjugate base. More the stability of the conjugate base, more will be the acidic strength of the acid. If conjugate base is weak, then its corresponding acid will be strong.